Okay, so hello, thank you for watching this movie. I'm Shotaro Shibafunai from Okinawa Institute of Science and Technology in Japan. This is my presentation movie for the online poster session of International Symposium on AIBS 2020. In this movie, I'm going to tell you about the extracted features of machine learning and its related physics. Okay. These days, the machine learning is widely used for data analysis. A lot of learning methods are proposed, but they can be classified roughly into these three types. Though, of course, that there are many techniques to improve each method. The main method in my talk is the second one, unsupervised learning. The machine is trained so that it can correctly reconstruct data after data compression, and that the output answers are reconstructed data. This is useful for extracting features of input data. As you know well, machine learning provides us a very useful tool, but some problems exist. We don't fully understand why the machine learning works so well. In other words, there are many neurons in intermediate layers or hidden layers, and they somehow process the information. But in general, is there some principle here? Unfortunately, we have no clear answer now. I think maybe this is my personal opinion, but the essential point is how the machine compressed the information. In unsupervised learning, the machine definitely does it. But even in supervised learning, as far as I know, the shallower layers behave like a data completion and extracting features of data. The reinforcement learning is a little bit different method, so I don't talk about it anymore in my talk. Okay, that's why I'm studying the feature extraction by machine learning. For physics researcher, including me, the completion of information reminds us of the coarse graining. This is closely related to the renormalization in statistical physics. In 2014, Mehta and Schwab pointed out they used the spin configuration in 2D Ising model. They can be black and white images like this. White is upspin and black is downspin. Then they found out that if such images are compressed more in the machine, the field of view of each hidden neuron is enlarged, like this. So this maybe correspond to the coarse graining, like the block spin transformation like this. Let's see, the left figure correspond to the original input configurations, and while the right figure shows the field of view of each hidden neuron. It has bigger view field compared with the original small size. Let me explain it a little more in detail. This is a sketch of machine learning they used. They input the 40 times 40 sized images of Ising configurations at the specific temperature here. Then then by unsupervised learning, the images are compressed by 20 times 20 hidden neurons, so that the machine can reconstruct the original images as well as possible. Then they have another unsupervised learning. They input the compressed here, the compressed 20 times 20 sized images. Then by another unsupervised learning, this image is compressed by the 10 times 10 hidden neurons. And they have another unsupervised learning, input this compressed 10 times 10 sized images, then by another unsupervised learning, the images are compressed by 5 times 5 hidden neurons. Okay. As we saw the fewer hidden neurons have a larger field of view. So the reconstruction process, then that after the learning, they reconstruct the configuration and like this, the complex 5 times 5 size images, then the reconstruct to the original size. Then this reconstruction process seems to the self-organizing. At least they have a larger field of view for fewer hidden neurons. That at least noise should be decreasing. Okay, the reconstruction result is this. The original configuration at the temperature being a little higher than TC, the critical temperature. But after such reconstruction, it seems self-organizing, at least noiseless, and qualitatively shows a coarse graining. Okay, this may be a kind of coarse graining. That's this author's claim. However, I thought that the relation to renormalization is not clear here. Please remember that the renormalization group or RG flow in two-dimensional Eisen model. In the very simplest case, simplest case means that without external magnetic field, like external magnetic field, and a coupling constant of nearest neighbor and sites is fixed. Okay, in 2D Eisen model, especially such cases, the behavior under the renormalization is well understood. The RG flow goes away from critical temperature TC and approach to T equals 0. This is a uniform configuration like this, or T equals infinity configuration, or the random configurations. Okay, the Meta and Schwab starts the configuration at the little above TC here. And they claim the reconstruction seems to self-organizing, means go to lower temperature. So, okay, this meant that the reconstruction by the machine seems to behave differently from RG flow. Okay, then it shows reverse, that goes the opposite direction. Okay, we are of course happy if the machine mechanism of feature extraction can be described in terms of renormalization, but this is the main question. But is it possible here? Okay, I will check exactly in my talk. For interest, if the machine learning reproduces the RG flow exactly, some tricks are needed. It's called the LSMI, or space mutual information, like this. However, this is not our case. Now we recognize that the machine called RBM, or restricted Boltzmann machine, which I explain soon, should extract features in a different way from the coarse graining and renormalization. In the following, we keep using this RVM of the simplest type, which is fully connected and has a single hidden layer. This is because I want to grasp fundamental understanding of how the machine learning works and extract features of input data. Hopefully, for this purpose, I use the simplest such machine. Okay, so let us move on to our experiments. This is our overview. First, we generate a spin configuration of Eisen model using the Monte Carlo simulation like this. Then we train a neural network. This is RBM actually, so that it output images as similar as possible to input spin configuration. This is exactly as unsupervised learning. Then after training, then the weights, it's a parameter of RBM is fixed. We input again the output configurations. Okay, doing this iteratively, input output and input output. This is iteratively, we obtain the flow of configuration. Okay, finally we can check if it's related to the RG flow or not. Okay, this type of a neural network is useful to extract features of input data, as I said. The neural network seems to compress the input data first, and then they reconstruct the data. Okay, then here we input the Ising configuration at various temperature or external magnetic field, TH. So the input configuration have some probability distribution of black and white or plus minus one patterns. Then we train the neural network so that it output the configuration with the same probability distribution as input data. Actually, this type of neural network is called the restricted Boltzmann machine, RBM. Okay, the probability of input configuration is exactly determined or defined, and that the probability of output configuration is defined like this using the energy function. This is the energy of input visible neurons or hidden neurons, and weight and biases here by Boltzmann distribution like this. Okay, that's why it's called the Boltzmann machine. Then we train the RBM. Train means optimize the weight and bias, the parameter of RBM, so that the KL divergence, Kovac-Leibler divergence, approaches the local minimum. Okay, the KL divergence is, as you know well, that as a distance between probability distribution and defined like this. This is a probability of input images, and this is the output images here. Then in our experiment, the input data, the spin configuration plus minus one, or black and white, and the value of hidden neurons is also binary plus minus one. This is a restriction for our experiment. Then the expectation value of hidden or reconstructed visible neurons are calculated as this. Then the output or reconstruct configuration plus minus one are obtained by replacing this expectation value with the probability like this to keep the same expectation value. Okay, this is a reconstruction process in my RVM training. Okay, then even after the training finished, the probability distribution of input configuration and output configuration are slightly different. This means that the KL divergence is practically not zero. This is very small, but not exactly zero. So if we input again the output configurations, we obtained another probability distribution like this of a reconstruction configuration. So doing this reconstruction process iteratively, we get the flow of probability distribution of spin configuration like this. Then we have questions. Does this RBM flow, or we call this flow of spin configuration is RBM flow because this is generated by the RBM. This RBM flow corresponds to RG flow, and how? The another question is that does it have the fixed point? The RBM flow has a fixed point of describing the features extracted by RBM. So the features should emphasize along the RBM flow. So if it has a fixed point, this should correspond to the feature extracted by RBM itself. Okay, this is a question, and this is here is the overview of our results. Actually, the RBM flow has it fixed points in the TH space and the temperature and magnetic field space. Actually, the no fixed point of spin configuration exists. This means that it is used for generated the new configuration at the specific TH. Okay, that spin configuration keeps changing, but it has fixed point in the physical quantity space like a TH. Okay, to estimate TH of output configurations, we use two ways. The first one is here, that we trained another neural network to output correct TH, parameter TH of input configuration. This is kind of the supervised learning. And the second one is that for only the H equals 0 configurations, we have the only parameter of the system, temperature T. So we can estimate this temperature T by calculating their energy of configurations. Because the energy and temperature have a monotonial 1-to-1 correspondence in this case, H equals 0 case. Okay, then this is a result for 2D, two-dimensional, and no magnetic field case. The RBM flow behave differently from the RG flow. Actually, the RBM flow approaches the critical point, around the critical point, while it goes away from T equals 0 or infinity, high temperature. This is exactly the opposite direction to the RG flow, like our expectation, but this is a result, and it's a very simple case. As in a more general case, we train the RBM with the one-dimensional or two-dimensional Ising configuration, including H equal non-zero, so the with external magnetic field. In this case, the RG flow approaches the fixed points in TH space like this. But the flow is different from the RG flow and its fixed points. Okay, let me explain it later. Okay, and if you are more familiar with the distributed representations or the output of hidden neurons than the physical quantities TH, and here are the results of PCA, principal component analysis of such representations. This is the distributed representation for input data, including the various temperature. This case, we have no magnetic field. Each single point corresponded each configuration. I also show here the distributed representations for only low temperature and very high temperature and the temperature around TC. Okay, then after iterative reconstruction, such representation become like this. You can see that such a pattern is quite similar to the temperature around TC here. Okay, then I think you can find such a reconstruction surely have a fixed point around TC because this reconstructed case is very similar to the TC case, the critical temperature of the Eisen model. Okay, so finally, let me discuss our results. Okay, the first, the RBM flow has fixed point. This is a very similar point to the RG flow, renormalization group flow. But the fixed points are in the space of TH physical quantities and not of configurations. Configurations has no fixed point. And because the features are emphasized along RBM flow, so its fixed points should describe the features of learning data itself. Okay, and especially in the 2D case at T equals 0, the fixed points exist at the same point, the critical temperature of Eisen model. But this is a very important point, but the flows go in the opposite directions. Okay, this means that T equals TC is a stable point in RBM flow, but unstable point in RG flow. Then this is our very naive proposal, but it is that the feature that RBM extract might be the scale invariance of configurations, because this is a very important and characteristic property of configuration at the critical point. Okay, then we want to have some evidence for this scale invariance. Let us compare the two kinds of RVM by analyzing the RVM flows and their weights. Okay, we restricted ourselves to, in this case, 2D and h equals 0 case here. The one is the RVM trained by configuration at only low temperatures. Okay, such a configuration has a large scale like this. And the other is that the RVM training, RVM learning at various temperature like this, including the low temperature and high temperature like this. This is the same as the previous result. Okay, then when the RVM learned only low temperature, the RVM fixed point is also in low temperature. In the latter case, as we saw, the RVM fixed point around the critical temperature, like TC, as explained before. This is a reasonable result. Okay, then let's see the eigenvalues of weights or products of weight matrices. Okay, that this is a product independent from the basis of hidden neurons. Okay, here the RVM, if the RVM learns configurations at the only low temperatures like this, the only few, around 5 eigenvalues are especially large. And if this is a latter case, if the RVM learns the configuration, the various temperature, including high temperature, all the eigenvalues have similar, not the same, but have similar values. I think that the many hidden neurons should be needed to learn the configuration of the various temperature or various scales. Here, this is our naive expectation. Okay, then let's see the corresponding eigenvectors to eigenvalues. Okay, this is first case, the RVM learning only low temperature, and that these 5 configuration has a large eigenvalues. The configuration with the largest scale have large eigenvalues. Okay, but the RVM learning the various temperature like this, the configuration, all these eigenvalues have a similar eigenvalues, and the configuration with the various scales. Okay, it includes a large scale and a small scale, but they have similar eigenvalues. It means that all of them appear in the reconstructed images. Then it may correspond to the scale invariance and the fixed point of RVM flow. Okay, this is a 2D and h equals 0 case. So then we can also discuss some general property of fixed points. The RVM learning both h equals 0 and h equals non-zero configurations case also show the difference from RG flow and the close relation to actually the thermodynamics. As you know, the configuration the T equals Tc and h equals 0 show the critical behavior of thermodynamic quantities like heat capacity, magnetization, like this. Especially we can see the blow up of heat capacity at T equals Tc and h equals 0. So the RVM flow in this case has fixed point with the special property of heat capacity. This is a result. Okay, this is a case of one-dimensional IC model. The RG flow goes in a unique direction, and okay, like this, and the fixed points are T equals h, th equals 0, 0, and 0, infinity, and infinity, T equals infinity. Okay, but the RVM flow approaches align points, and their fixed point can be fixed by these fixed points can be fit by the maximum heat capacity. Okay, so the two flows are considerably different. Then this is a case of the 2D Eisen model, and the RG flow has a critical fixed point only at the T equals Tc and h equals 0, as I said. The RVM flow in this case approaches the aligned point like this. This is a fixed point. that these fixed points, RBM fixed point, are coincident again with the local minimum of heat capacity like this, which can be numerically calculated using the Monte Carlo simulation, because we cannot have any analytical result in this case. Okay, the maximal heat capacity include the critical point, of course, here T equal Tc and H equals 0. So the maximum heat capacity is a kind of generalization from the critical point. Okay, there are the crossover point of two phase, because phase transition. They're not exactly this scale invariant, but has similar property. Okay, so we can assume it is a kind of generalization. Okay, finally, let me check that the parameter dependence. Okay, and finally, let me check that the parameter dependence. The RBM fixed point depends on the various parameters like temperature of training data or number of hidden neurons and so on. But fortunately, the RBM fixed point is at around Tc, critical temperature, in wide range of NH over NN, the hidden neurons or visible null. Yeah, especially at the NV over NH equal 4, the fixed point here, the fixed point seems independent from temperature of data and appears around Tc at the critical temperature here. This case, NV over NH equal 4, reminds us of 2 times 2 Bloch spin transformation like this. The Bloch spin transformation, as I said, is closely related to RG flow. Then, as a one indirect evidence, the RBM fixed point, RBM weight matrices here tells us about the correlation among the spin sites in the reconstruction or RBM flow. And this is NV called 20 times 20 case, and NV over NH equal 4 means this orange one, NH at 10 times 10 case. So if the NV over NH equal 4, the spin with the distant smaller than 2 are correlated. So this is a very similar situation in 2 times 2 Bloch spin transformation. And actually, we are trying to find additional more evidences of RBM flow and Bloch spin transformation now. Okay, this is a summary and feature direction. We perform machine learning of the RBM to extract the features of spin configurations and in Eisen model. Then we find that the RBM flow of reconstruction has a fixed point, which should correspond to the features extracted by RBM, just as a RG flow, but their behaviors are obviously different, especially the directions is completely different from each other. Then we propose that the features that the RBM grasps may be the scale invariance at the critical point and the maximum heat capacity. In addition, the RBM reconstruction seems to relate to Bloch spin transformation or renormalization. Then in the future, we need to discuss also the H equal non-zero H region. But even in this case, at least around the T equal Tc and H equal 0, the RBM flow and RG flow go in the opposite direction. So I'm now studying more the direct relation of RBM flow and RG flow in this case. Okay, this is the end of my presentation. Thank you for watching.